All right, 14.4, last section of this module 14. Changing a little bit, so still dealing with lines, but now we're adding perpendicular lines. Our essential question: what are the key ideas about perpendicular bisectors of a segment? So, perpendicular bisector theorem states if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So what essentially that states is if I have a segment here and then another segment here, perpendicular means we're going to have right angles, and it's going to bisect that line so that we have two equal parts. And then it also states that this become congruent as well. All right, so given P is on the perpendicular bisector M of AB, we want to prove that PA is equal to PB. So we want to consider the reflection across line M. Then the reflection point of P across line M is also P. Although that sounds a little confusing, all it's saying is that since point P lies on line M, that when we reflect it, it's still on that same line. So we're just stating point P is point P, but the reflection part is what comes next. That's important. Also, the reflection of point A across line is B. So as we take this point here and when we reflect it over here, that then becomes A, but it lands on B. And so by that is by definition of reflection. Therefore, PA is equal to PB because reflection preserves distance. And essentially what we did is we took A here and put it over here. So this was PA, that is PA. So those have to be the same. Just over here, this A is actually B. All right, reflect. What is the conclusion you can make about triangle KLJ and the diagram using the perpendicular bisector? So you guys have that in your notes. That's a quick sketch here. Not perfect, but we have this here. Hey, what can we state based on what we just talked about? And we'll discuss that when we come into class. Now the converse of, and that symbol there represents perpendicular. And it's mathematical symbol for perpendicular bisector theorem. So this states if a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector of the segment. So remember, converse is just flipping your if and then. Previously we said that if a point's on a perpendicular bisector of a segment, then it's equidistant from the endpoints. Well, now what we're stating is if a point is equidistant, then it is a perpendicular bisector. Okay, so those are good ones to know. Now we're going to jump into a proof here. So we want to prove the theorems about right angles. So we have a diagram over here. We have one angle that we know for sure is 90 degrees. And what we want to prove is measure of angle 2, 3, and 4 are all 90 degrees as well. So first one should be hopefully fairly straightforward. It is given. And then 1 and 2 are a linear pair is also given because you can identify that in the diagram. And then 1 or 2 are supplementary. That is because they are a linear pair. And then measure of angle 1 plus measure of angle 2 equals 180. That is definition of supplementary. And then since we are told up here in step 1 that measure of angle 1 equals 90, we can then substitute that in. So that is substitution. Property of equality. And then we subtract that 90 over, so that is subtraction property. And that gives us our first one of measure angle 2 equals 90. Then measure of angle 2 equals measure of angle 4. And the reason for that is if we look at that, those are vertical angles. And then by substitution, replacing measure of angle 2 with 90, that gives us measure of angle 4 equals 90. And then again, we're looking at measure of angle 1 and measure of angle 3. Those are vertical angles. And measure of angle 3, we now replace measure of angle 1 with 90, and that gives us our last one. And our reasoning is substitution there. So now we just proved all 4 angles are 90 degrees. Next, if 2 intersecting lines form a linear pair of angles with equal measure, then the lines are perpendicular. So given measure of angle 1 is equal to measure of angle 2, we want to prove that L is perpendicular to M. So by the diagram, 1 and 2 form a linear pair, so 1 and 2 are supplementary by the linear pair theorem. And by the definition of supplementary angles, measure of angle 1 plus measure of angle 2 equals 180 degrees. It is also given that measure of angle 1 equals measure of angle 2. So measure of angle 1 plus measure of angle 1 equals 180 by, we replace 2 with 1, and that is substitution. Adding gives 2 times measure of angle 1 equals 180. And measure of angle 1 equals 90 by division property. So all we did is we took that 2 and divided by 2. That gives measure of angle 1 equals 90. Therefore, angle 1 is a right angle, and L and M are perpendicular by definition of perpendicular lines. Because definition of perpendicular lines means 2 lines that intersect giving you a right angle. We just proved it had a right angle, so therefore L and M are perpendicular. All right, say that the converse of the theorem in part B is the converse true. So going back and looking, again as a reminder, it's the theorem that says if 2 intersecting lines form a linear pair of angles with equal measures, then the lines are perpendicular. So you can go back and look at that, write the converse, and then state if it's true. We'll discuss that in class. All right, your turn to apply some of this. So we have a couple of parallel lines. So B is parallel to D, C is parallel to E. Measure of angle 1 is 50, measure of angle 5 is 90. Use the diagram to find measure of angle 4. We'll work on that in class. And one more. AD is 10 inches long, BD is 6 inches long. Find the length of AC. And then our essential question, what are the key ideas about perpendicular bisectors of a segment? And the last year assignment, page 714, 1, 5 through 8, 10 through 14, and 17.